All right, so we are moving on with section 3.1b here, talking about something called the correlation or correlation coefficient of a data set. Before we jump into that, I have a vocab word that probably should have been in the last set of slides, but I forgot to talk about it then. And it is the word bivariate, which sounds really fancy. But all bivariate means, bi is two, so it's a two variable data set. So anytime you're doing a scatter plot problem, you might see it referred to as bivariate data, which sounds really fancy. All it means is you have two variables. So just a little vocab word to kick off our lesson. Let's get into our new concept for this video, which you have heard about before in Algebra 2, which is the idea of a correlation coefficient, which is also sometimes called the correlation R. First, a quick explanation of what it is. It is going to be a measure between -1 and +1 that describes the direction and strength of a linear association or a linear relationship. And I'm going to underline the word linear a couple of times. So I'll get back to that in a second, but let me go ahead and remind you guys of what this is, because you did do this with me in Algebra 2. We would have in our notes a little number line with -1 over on the left side, +1 over here, and 0 perfectly in the middle. When you look at your correlation coefficients, the closer it is to the edges of your number line, so the closer it is to a +1 or to a -1, if you have a +1 or a -1, your points line up absolutely perfectly. So a +1 correlation would mean a perfect positive line. It doesn't tell you anything about the slope, so it could be like this, it could be like this, but it's a perfect line and it's positive in direction. And then over here at -1, you'd have a perfect negative line. So again, going downwards perfectly in a line. And if you're absolutely 0 in the middle, that's no correlation at all. So that means your points are a complete scatter would be one way of saying it, just a total mishmash of points. But there are other possibilities that I'll talk about in these slides. And then you could be anywhere in between. So what I have right here on the side is like a little rule of thumb for us to use right here. Not every textbook agrees. Like you could go to one textbook and this one calls 0.40 moderate. You could have somebody else who argues that's really moderately weak or something like that. So it's not like set in stone, but this is a good set of guidelines that you guys can use. And you can have things like moderately strong and stuff like that too. But just to give you an idea of where those numbers would fall. Anything from 0.8 and above is really, really strong. In real life data sets, that doesn't occur all that often. If you have something in the 0.6 to 0.7 range, that's still pretty strong for actual data and enough to like get somebody's attention. So in all of this information right here, just realize that this is talking about a linear relationship or a linear association. This section with R is like a multiple choice test writer's dream section because there's so many misconceptions kids can have that a multiple choice question can just trip you up on. And we'll talk about those as we go through our slides. So before we get into rules and kind of common errors and trip ups here, I want to spend a little bit of time practicing and learning just by looking at a picture, like getting a gut sense of like what R should be for a graph. A lot like we did when we learned about standard deviation, how I wanted you guys to be able to just look at a graph and have a sense of what the standard deviation is. Same thing with R. And we'll end up doing a little in-class competition with this, similar to what we did with standard deviation. So this graph right here, if you look at it, just lots of random scatter, not much going on, no real consolidated pattern. If I had to say, it maybe there's a slight downward tilt to this data set right here, but R is going to be really awfully close to 0. So I'm going to call this about R is like -0.01 or -0.05 or something like that. It's almost perfectly 0 for this one because the points are just no pattern, no linear pattern going on. As you move to this graph, though, you start seeing more of a downwards pattern. Certainly the points are pretty spread out, but they are moving in a downwards direction here. This guy is somewhere in the neighborhood of a negative 0.3 or negative 0.25, somewhere like that. So I'm going to call that about a negative 0.25. Again, R is negative because the points are going downwards. This next guy right here, as you go, like the pictures go, they get consistently more packed together. This next one is somewhere in the neighborhood of a positive 0.5. Oops. Positive 0.5. This guy is a negative 0.7. This next one is actually a positive 0.9. So the points are pretty closely packed together as we go right here. And this last one, believe it or not, is about a negative 0.9899, somewhere in there, really close to a line when you get there. So you guys should be able to build an intuitive sense of like what R is going to be just by looking at the points in your data set. And we will practice that on the next slide right here in class and do a little competition to see who's the best at estimating R. So we'll have a chance to do that in class, but let's move on and talk about misconceptions and things that kids do wrong. One very common thing that I see a lot is the idea of using R to assess how linear a data set is going to be. So a problem would say something like this. You wouldn't see the pictures there. Just pretend like those pictures aren't even here. What graph is more linear? A graph with R is 0.41 or a graph with R equals 0.97? And everybody's first instinct is, well, the 0.97, it's way closer to 1, so obviously that must be linear. But that is not always the case. This graph right here is a part of a parabola. You can see that there is very obviously a nonlinear or a curved pattern going on with these points right here. But if you drew a line of best fit through that data set, that line does do a pretty good job, and those points are pretty close to the line in general. This parabola half right here actually has a correlation of 0.97. On the other hand, these points right here, nothing special going on, but if you look, there's nothing better than a line right here. This data basically is linear because there's no other pattern that's going to help us out better to figure out what's going on. This data set only has a correlation of 0.41, okay? So when you look at R does not give us info about form. Okay, so let's go back to the first slide. If you guys flip back in your notes, we wrote in our definition for R that R talks about strength, and R also talks about direction. Strength, how close is it to 1 or negative 1? Direction, is it a positive R or is it a negative R? Strength and direction are fine. R does that for you. But R only assumes the data set can be, like it's assuming your data set is linear when it looks at it. So all it does is it tells you how good of a job a line is going to do. Just because you have a high R doesn't mean your data set is linear. I would call this second data set linear because there's nothing better going on. I would not call that first data set linear though, because it is curved. So a multiple choice question will basically be like, oh, which of these data sets is more linear? And all they'll do is show you two R's. You cannot tell which data set is more linear just by looking at R. It's going to happen on our chapter test. There will be a multiple choice question that does basically this trick right here. And some of you will fall for it because you're going to move too fast through the question. R cannot tell you about form. Okay? So that's an important misconception that comes up a lot. So on the bottom of this slide right here, you'll see a formula for how you actually calculate R. We've never talked about that before in Algebra 2, like where R comes from. The calculator just kind of gave it to us. Even in AP Stats, we are not going to calculate R itself because it's just a mess. It's just too much to do right there. And a calculator or a computer in real life is how you're going to get that information when you use R to do whatever it is you're doing with your research. But with that being said, I do want to point out something with regards to this right here. If you look at one of these little pieces right here, this bottom one that's hidden behind my little toolbar right there, has the sum The sum of, and it goes xi minus x bar over s of x, and then it does the same thing with y being multiplied together. So the bottom one is just with i's in it. On the top one, they broke it up into little chunks for each term. So it's the sum of each of those pieces. If you look at what's going on inside of each of these pieces right here, you're going to take an x value. You're going to subtract the mean of the x's, x bar, and you're going to divide by the standard deviation of the x's. After you do that, you're going to take the y on your same coordinates. You're going to subtract the mean of the y's, and you're going to divide by the standard deviation of the y's. So if you think about, like, that should look a little familiar to you guys. Where have you seen that before? That's exactly what a z-score does, value minus mean divided by standard deviation. So when you calculate r, what's basically happening is you take a little z-score for your x-coordinate times a little z-score for your y-coordinate, and then you do that for each of your separate points. You add them up, and you divide by that n minus 1 like you would do when you calculate standard deviation. So this is very similar to how we calculate standard deviation. So it's very similar to z-scores and standard deviation. You will never in my class be asked to calculate this yourself, but you can sort of at least appreciate what it is that's going on right there. So let's move on and talk about some other stuff that I find kids mess up on with regards to R. Again, all of this stuff on this slide right here is like a multiple choice questions dream. People mess up on all these little things a lot. So let's talk about some of these here. When you look at correlations, that's R. Sometimes you'll hear it called the correlation coefficient. Sometimes it'll just say correlation. Sometimes it'll say correlation R. All means the same thing. It makes no distinction between explanatory and response variables. What does that mean? If you switch X and Y in a problem, you're going to still get the same R. So if I was graphing, like in the last video, I did a problem where I did, I think it was sprint time versus jump distance. If I were to swap those and put sprint time here, jump distance here, the picture is going to look different, obviously, because I've moved my variables around, but the R that you get will be exactly the same. So if you trade your variables, R stays the same. R also is not impacted at all by units. So that one, I don't need to add any context. It makes sense as is. R does not change when you change units. So I did my problem, I think it was in inches for a long jump distance. If I wanted to make that feet instead, naturally my scaling is going to be different. R won't change. And R itself does not have any units on it. So R is not affected by units, and R does not have units. So you'll report R is 0.8 or R is 0.4, sorry. Never a 4, because it's always between -1 and +1. No units on R. Okay, a couple other things going on right here. Correlation means that both variables must be quantitative. So correlation goes along with scatter plots, hand in hand. You would not talk about correlation for two categorical variables. So we talked about like year in school versus like freshman, sophomore, junior, senior versus prom, opinion, or whatever, all those problems we've done. When you make a conditional distribution, you cannot have R. R is only for quantitative variables. It does not talk about curved relationships, no matter how strong it is. It is not, I'll get to that next one, sorry. Does not talk about curved relationships, no matter how strong it is. I can't remember. Let me see if there's another slide on this. There is, but not what I meant. You can have a picture that's a perfect full parabola right here. So if I have a data set like this, the R for this problem is actually R equals 0. So as soon as you see R equals 0, don't think it automatically has to be just a cloud of points. This is R equals 0 as well, because if you draw a line through it, that line is going to be absolutely awful. So a problem can still have a pattern and have a low R, because R only measures linear patterns, not curved patterns. R is also strongly affected by a few outliers or unusual points. So if you have a couple points that are outside the general trend, that does mess with R. So like, let's say I had a data set going like this. R is going to be pretty high right now, like 0.8, 0.9, somewhere in there. If I toss a point that's way outside the pattern, that's going to bring down R a fair amount. So that would go from like 0.8 or 0.9 to maybe like a 0.4 or 0.5. So an outlier or two or a point or two that's way different will affect R quite a bit. We'll do more with that in our last video of the chapter. And finally, correlation is not a complete summary of two variable data. You need to do other things too to get the full picture. R doesn't tell you how linear your data set is. You always want to be able to look at a graph and do more. Like R is not just the full package. It just helps with other pieces to fully understand what's going on. So my last slide right here is a phrase that I'm sure you guys have probably heard before. It's an extremely famous, popular phrase. Correlation doesn't equal causation. In other words, just because R is high doesn't mean that one variable causes the other to occur. Two examples of that. Looking at ice cream sales versus number of shark attacks, obviously you can think about that and say selling more ice cream isn't going to cause shark attacks. But in months where there are higher ice cream sales, when ice cream sales go up, shark attacks also go up. The reason for that is ice cream sales go up when you have warmer weather. And when you have warmer weather, more people go into the ocean, and then there's more chance for sharks to attack people. So you can have other variables hiding behind the scenes that are really the causative variable in that problem. Just because R is high doesn't mean you're going to have to necessarily say one causes the other. Another example, if you look at the amount of chocolate consumed by citizens in a country versus the rate of Nobel Prize winners that that country has, the correlation between that, if you actually look at that data set, it's apparently a 0.791, which is really high for like real life data. More chocolate obviously doesn't cause there to be more Nobel Prize winners. And if you guys think about it for a second, what variable could be behind the scenes kind of influencing how many Nobel Prize winners a country has? It ends up being kind of income or just the wealth of the country there, because wealthier countries have the ability to eat more chocolate, buy more chocolate, and wealthier countries have the resources to train more Nobel Prize winners. So just because R is high does not mean that one variable causes the other. You would need to do an experiment with random assignment to be able to talk about cause and effect. And then finally, we have a nice little comic here to wrap things up. The guy says, I used to think correlation implied causation. Then I took a statistics class, so now I don't. And then they're like, oh man, it sounds like the class helped. It caused you to have that belief set. And then he says maybe because he knows there was no random assignment. It's just so great. So yeah, just remember, R can be tricky. There are a lot of places where you can have misconceptions. So be careful when you use R to analyze a data set.